Okay, so we need to talk about elastic versus inelastic collisions, and we're going to look at examples of both of these in a moment. But okay, so in an elastic collision, the objects bounce. That's fine for us today. Okay, so we're going to keep things simple. And if we're going to say that if they bounce off each other, like billiard balls bouncing off each other in a game of pool, we're going to call that an elastic collision. Now, technically, to be truly elastic, they have to bounce off perfectly with no loss of kinetic energy. We haven't studied kinetic energy yet, so when we get there, we'll kind of flesh this out a little bit. But for now, it's enough to say that it's an elastic collision if the two objects bounce. Now, the other kind of collision is an inelastic collision, meaning not elastic collision. And in that case, they stick together. Again, this is a bit of a simplification, but that's what we're going to say. If they stick together, it's inelastic. Now, again, technically, it's inelastic if any kinetic energy is lost. So technically, they can bounce off each other to some degree, but they will always heat up. The two objects will always heat up, and they may be permanently deformed. So a good example of an inelastic collision is a fender bender or a car wreck where the two cars run into each other and they crush into each other and they stick together in one chunk of metal, or two balls of Play-Doh flying together and splatting together and sticking together. That would be a perfectly inelastic collision. And again, today we're going to simplify it and say that in an inelastic collision, they just stick together and go along. We're not going to worry about the gray area here. Okay. So first, let's look at, oh yeah, this is a key idea. Remember this. Momentum is conserved in all collisions, whether they are elastic or inelastic, because the law of conservation of momentum is the law of conservation of momentum. Students sometimes get confused by this. They think that it's conserved in elastic collisions. Momentum is conserved in elastic collisions, maybe not in inelastic. Remember this, please. Momentum is always conserved, always, whether it's an elastic collision or inelastic, always. Okay, so first now let's look at an elastic collision where two objects bounce. Let's just go straight to the clipboard here. Here we are. Okay, so suppose we have an elastic collision where we have two objects that are flying together and they bounce off each other and they go their merry way. How can we use that conservation of momentum equation to figure out what's going on? So in this example, we have a 6-kilogram ball flying at 10 meters per second. It's approaching a 2-kilogram ball going the opposite direction at 20 meters per second. That's why I have it minus 20. That just means it's going the opposite way. They collide, they bounce off each other, and after the collision, the heavy one is going back the way it came at 5 meters per second, so it bounces off, and the 2-kilogram ball goes bouncing off to the right. And we want to figure out what is the speed of the 2-kilogram ball. Okay? And we're going to use our conservation of momentum equation. So m1v1 plus m2, I can talk but not write at the same time, m2v2, that's going to be the total momentum before, and that's going to equal the total momentum after. So m1v1 after plus m2v2 after. And now we just start plugging in values. So we're going to call this one object 1 and this one object 2. This is object 1, this is object 2, just to keep them sorted out. So we have 6 kg times 10 meters per second plus 2 kg times negative 20 meters per second. It is very important in these to keep track of the positives and the negatives and to carry them through. It really does matter. It doesn't work if you don't do it that way. So we've got to do the minus 20. And that is going to equal 6 kilograms times negative 5 meters per second plus 2 kilograms times V2. So we have everything with only a single unknown. Now it's just a matter of crunching the numbers. So we're going to get 60 minus 40 equals negative 30 plus 2v2. 60 minus 40 is 20. 20 plus 30 is 50, is equal to 2v2. So 25 meters per second is equal to the final speed. And it's a positive 25, so that means that it is going away. It is going to the right. Okay, now how can we check to see if we're right? Well, we can plug in numbers and make sure that we've got this. So we just knew 60 minus 40 is equal to negative 30 plus, let's see, so we have 2 times 25, so this is going to be plus 50. That turns to be 50. So 60 minus 40 is 20, and negative 30 plus 50 is also 20. So the total momentum before was 20 units. The total momentum after was also 20 units. That's all there is to it. Okay, now what about an inelastic collision? What about an inelastic collision? And for this is one where the objects hit and stick. And for this, we're going to kind of run our cannon problem in reverse. Slightly different numbers, but kind of the same idea here. So what if we have our cannon, which is now going to be rolling forward at 1 meter per second, and a cannonball comes sailing in from the enemy at 1,500 meters per second. It goes right down the barrel and sticks in there. Okay? So we have two objects which collide and stick together. What is going to be the velocity of the cannon after that collision, which is an inelastic because the two things stick together? Okay, so we're going to start off with the same equation, but there's something more we can do with it since it's inelastic, which will help us out a lot. So let's start off with the basic one. So m1v1, this is the momentum before, plus m2v2. We're going to call the cannon object 1 and the ball object 2. Get that back where it was. And that's going to equal the momentum after. But here's the thing. Since they stick together, that means that the velocity for both objects is the same. In other words, since it's inelastic, V1 equals V2 after the collision because they've stuck together. Okay? So we can call those V final. V final is the speed of the first object and is the speed of the second object because they're the same. So that means that we can, well, okay, I'll do the derivation here. So it's going to be m1 v1 plus m2 v2, but v1 and v2 are the same. So that means we have m1 times v final, that's the final speed, plus m2 times v final, because those are the same. We can factor out the V final and we can make M1 plus M2. In other words, the total mass is going some speed. Okay, so this is just derivation stuff. The equation that you use for inelastic collisions is the same on the left because this is still the momentum before. This is P before. But the term on the right for inelastic is the total mass, m1 plus m2, times whatever, however fast the whole thing is going, the final speed of the lump, if you will. So in this case, to start plugging in numbers, we wind up with 1,000 kg times 1 meter per second plus 2 kg times negative 1,500 meters per second, and that is equal to the total mass, m1 plus m2, that is 1,002 times the final speed, because both objects are now going the same speed. Now we can crunch that together. We get 1,000 minus 3,000 is equal to 1,002 VF, negative 2,000. Let's see, is equal to 1002 VF. So we get 2000 divided by 1002, and we get 1.996 meters per second equals the final speed. And it's going to be a negative number because that's negative. It turns out that the ball has more momentum than the cannon itself. So it actually hits the cannon and pushes a 1,000-kilogram cannon backwards a little bit. And that's the answer. All righty. So what have we covered? Let's go back to our slideshow here. Remember, this inelastic collision that we just did only works because the momentum is conserved in an inelastic collision. That's the only reason we know that one side of the equation is equal to the other side of the equation. Absolutely essential. Let me make sure I haven't left anything out here. I don't think I have. These are just other examples that I use on the smartboard. Yeah, we're all good. Okay. So we learned about conservation of momentum. We demonstrated it by thinking about a cannon that is firing. We saw that momentum is conserved always, always, always in all systems. Momentum is conserved. If momentum leaves one object, it has gone to another object. If it appears in one object, it has come from a different object. That's just how it works. We distinguished between elastic versus inelastic collisions, and we learned equations that work for each of those. And this is going to get you ready for the lab. So the lab that you're going to do is, let's see if I can get it out here. Do I want to do this? No, I think that the lab is going to speak for itself. I'm certainly going to try that, and we'll see what we can do. So that'll do it. All right, we will see you next time.